Hey guys, and welcome to this WACE Academy online lesson on circular motion. This will be covering dot point number 8 of the physics syllabus, subunit gravity and motion. To begin, we'll cover uniform circular motion, and then circular motion velocity. Thirdly, we'll learn about centripetal acceleration, before ending with centripetal force. Newton's first law states that an object travelling in a straight line at constant speed has no net force acting on it. However, what's happening when that object changes direction or turns a corner? Well, there must be some sort of force acting on it, as it's changing direction, which we consider an acceleration, which I'll explain a little bit later. This force that causes the object to turn in circular motion is called centripetal force. It can come from a variety of sources, but in each case the net force is always acting perpendicular to the direction of motion, and is directed toward the centre of the circular path. Let's look at some examples. So when a car goes around a roundabout, the force is being supplied by the friction between the road and the tyres, directed towards the centre of the roundabout. When a yo-yo is swung around by its string on a finger, the tension in the string provides the force. And when a satellite orbits the Earth, it's the gravitational force that provides the centripetal force. If centripetal force is constant through this circular motion, then we achieve something called uniform circular motion. Uniform circular motion is defined as the motion of an object travelling at constant speed on a circular path. At any time, the net centripetal force will be the same at any other time. If this force changes at any time, then the circumference of the path will change, and we will no longer get a perfect circular path. We know that velocity is the distance an object covers per unit time, which is easy to calculate when it's travelling in a straight line. But what about a circular path? Let's take a look at the path of this object, travelling through a circular path with radius r. Let's say it takes the object t seconds to complete one full circle. Well, we know the formula for the circumference of a circle is 2 pi r. So the formula we can use to calculate the velocity of circular motion is v is equal to 2 pi r over t, with velocity being in meters per second, radius in meters, and t in seconds. Let's look at an example. Let's say we're asked to calculate the velocity of an object that takes 1 minute and 4 seconds to make a complete circle around a circular path with a diameter of 0.5 kilometers. Okay, so let's begin with t. We know that it needs to be in seconds, so let's convert 1 minute and 4 seconds. 64 seconds. Now let's do the radius of the circle. So we're given the diameter in kilometers, so let's convert it to meters first. 500 meters. And then we'll divide it by 2 because we know the radius is half of the diameter. So now all we have to do is plug in these numbers into the equation and we're done. .53 meters per second. The next property of circular motion we're going to learn to calculate is centripetal acceleration. You can just pretend this is a fancy way of saying circular acceleration, but the reason it's so important is that every single object in circular motion is accelerating, even those travelling at a constant speed. Why? Well, remember that acceleration is any change in velocity, and because velocity is a vector, which means it has both a magnitude or size and direction. So, if we change the direction, even if the magnitude is constant, we have to call this an acceleration. Okay, great, but how do we calculate it if only the direction is changing? Well, that's where this equation comes in. Centripetal acceleration equals velocity squared over the radius of the circular motion. And these are the units. We're going to do an example soon, but before that, let's learn the next equation, which is for centripetal force. Now, I know at this point, it sounds like I'm just adding random words onto centripetal. But if you think about it, if an object has acceleration, and force is equal to mass times acceleration, then surely the object has centripetal force too. So this is the equation for centripetal force. You might notice it is actually quite similar to the formula we just learnt. Specifically, it's centripetal acceleration just multiplied by m, which fits the F is equal to ma equation I'm sure you're all familiar with. You can see how the centripetal acceleration formula fits into the centripetal force equation when I highlight it in green. Okay, so time for the practice question. Calculate the centripetal acceleration and force of a 900 kilogram car travelling around a roundabout with a diameter of 10 metres. The car maintains a constant speed of 20 metres per second. As per usual, first we'll pull up the equations we'll need to use. So this will be centripetal acceleration and centripetal force. Then we're going to make a list of all the variables we need to know and fill in the ones we already know. The mass of the car is 900 kilos, its velocity is 20 metres per second, and the diameter of the roundabout is 10 metres. But be careful, we need radius, so 5 metres. Now just plug these variables into the equations and we'll get our answers. So the centripetal acceleration of the car is 800 meters per second. And the centripetal force is 72,000 newtons. That brings us to the end of the lesson. I hope you enjoyed it, and I'll see you next time.